We're going to turn our attention, pardon me, to finding area between curves rather than just under a curve or between a curve and the x-axis. You can see here we actually have two different graphs, and the idea that I'm going to explain is that we're looking for the area of the shaded region. You can see it's bounded on top by the graph of f, and it's bounded on bottom by the graph of g, and it's between the two x values a and b. Now, before we actually set up a problem like this, we need to understand how we can calculate distances, because recognize we're going to do this in a very similar fashion to what we've done in the past, is we're going to imagine a representative rectangle here. Okay, and of course that representative rectangle will have a width that's infinitely small, what we call dx. But the question ends up being, what is the height? And of course the height changes obviously as we go from A to B, but how will we calculate the height in general? Now before, when we talked about the height, it was actually just the value of the y value of f. And we only had one y value involved here. How far that y value is, of course, from the x-axis, either up or down. Of course, here, this isn't going from the x-axis, so we need to understand a little bit about how we calculate distances or heights. So let me just let me draw a little diagram over here, just to have us to give us something to refer to. And let's suppose this is where 0 is. Let's say this is 1, this is 2, this is 3, this is 4. Down here's -1 and -2, and say -3. Now, if I have a line segment that is measured right here, so suppose this is my line segment, we can look over to our scale on the left and we can count from 1. Oh, from 1 we go up 1 unit, 2 units, 3 units, and we can calculate 3 units. What I would like you to recognize, though, we don't need to count. What we could take is this highest value of y, which is 4, and from it subtract the lowest value of y, which is 1, and we would get a value of 3, which is in fact that height, isn't it? That is 3 units. Now, suppose that our measurement, or let's say, suppose this line segment fell below the x-axis. So we would have a line segment here, and of course the lower part is -3 and the higher part is -1. And we can clearly see that that distance is 2. But when we don't actually know the values, how could we calculate it? Well, we do the same thing. We take the highest y value, which is -1, and subtract from that the lowest y value, which is -3. And of course, -1 subtract -3 is the same as -1 plus 3, which is a positive 2 again. Or not again, but a positive 2. So although we could visualize it here, we could calculate it as we have done. Now, what would happen if part of the line segment was above the x-axis and part was below? Suppose we had something like this. Now, again, we can count, let's see, how many, from -2, we go to -1, that's 1 unit, to 0, that's 2 units, to 1, that is 3 units, to 2, that is 4 units, to 3, that is 5 units. We can count it, but we're going to be in a position where we need to be able to calculate without having to count, because we don't really know what all those values are necessarily going to be. So we go about it the same way. We take the highest y value, which is 3, and subtract now the lowest y value, which is -2. Well, 3 subtract -2 is the same as 3 plus 2, and so that distance is 5. And so we can calculate then by taking the highest y value, subtracting the lowest y value, whether positives or negatives are involved, does not matter. We'll still get the height or the length of that line segment, won't we? So when we look up here at the graph that we started with, now we know that that rectangle that I've sketched in and made darken, remember, it's infinitely narrow. and that infinitely narrowness, that width, is why we call that dx. But if we look at the height, see the highest y value, just imagine right here, that y value is represented by f of x, isn't it? And the lowest y value that is right here on that rectangle, see, we're trying to find out how high that rectangle is. Well, that lowest y value is represented by g of x, isn't it? And so if we wanted to know the height of that rectangle, okay, then we would take the highest value, which is f of x. Let me just come up here because I've run out of room. We'd take the highest y value, which is f of x, and subtract the lowest y value, which is g of x. And that would represent the height of that rectangle. And you can just see that that's the function on top, subtract the function on bottom, isn't it? But now remember, the way we calculate area is the integral sign is telling us that we're infinitely adding. We're going to add up an infinite number of infinitely areas of infinitely small rectangles. And of course, we're going to start these rectangles when x is a, and we're going to stop these rectangles when x is b. We're just thinking about taking infinitely small rectangles and moving them along through that area, aren't we? So that we scoop up all of the area with those infinitely small rectangles. But the area of one single rectangle will be its height, which we've just determined here is f of x minus g of x, times its width, which is just dx. And so this gives us the form, if you will, for the way we'll calculate the area between two curves, not under a curve. Now, you might also recognize when this is all said and done, this function f of x is the bottom, is the top line, isn't it? Oh, my bad here. That's the top function or the top curve. And this g of x that we're subtracting ends up being the bottom curve, doesn't it? As we saw here. The highest subtract the lowest. Well, that kind of gives us an idea of how we're going to do these problems. So let's get set up on the next page and we'll actually begin one. Okay, you can see example 1. We're to sketch the graphs of f of x equal x squared minus 4 and g of x equal 2x minus 1, and then find the area of the region bounded by the graphs and the vertical lines x equals 0 and x equal 2. Of course, this just means, when we see this, we just mean between x equals 0 and x equals 2, don't we? That's really what that's telling us. Between those two x values. Okay. Well, I've already got the, if you will, my graph paper set up. And sometimes the part of graphing is the most important part of the whole thing, and also the most challenging. And sometimes we can come up with a real quick sketch, and that's good enough. Sometimes we need to be a little more precise. So I'm going to start out relatively precise here. And one thing that we need to be aware of, if you recall, is that we have to really know how to calculate the height of a representative rectangle. And so that means we need to really know which of the two functions are on top, what the top boundary is and what the lower boundary is, the bottom boundary. And just because our functions are called f and g, that doesn't mean the function f is on top and the function g is on bottom. We don't know that until we make our graph. And so that's the reason the graph becomes so important. Well, if we just consider f of x equal x squared, okay, minus 4, we should, at this point in our math career, understand that that's a parabola that opens up, and it's actually been shifted down 4 units. So that means the vertex is down here at -4. See, we ought to recognize the vertex is has a x value of 0 and a y value of -4. Okay, and actually we could find that using calculus, couldn't we? See, well, I apologize for taking a kind of a detour here, but we know it's a parabola, and the vertex would be either a relative maximum or a relative minimum, wouldn't it? So that's what the vertex would, where a vertex would occur. And so, and in this case, we really know we have a relative minimum because we know it opens up. We already know that. But to find the x value of the vertex then just means we'd need to take the derivative of our function. And remember, relative maximums and minimums occur where the derivative is equal to 0. And so we could set that to 0, and when we solve, we get x equals 0. And then after we get x equals 0, then the y would just be f of 0, wouldn't it? And in this case, that's 0 squared minus 4, and that is our negative 4 value. And so we have our x value of 0 and our y value of negative 4, and we did that using calculus if we didn't already remember that. Okay, now, so here we have our derivative, our vertex down there at 0, negative 4. We need a few more points to get a reasonable graph. And we could do that very quickly, couldn't we? By just making a solutions table. That is, we'll pick a value, for instance, maybe pick a value of 1 for x. And when we do, we would calculate y to be negative 3. We just put 1 into the function, and we'd get 1 squared minus 4, which is negative 3. And we could pick a value of 2 for x. And when we do, then we would get a y value that was 2 squared minus 4, which is 0, isn't it? So 1, negative 3, which would be this point, and 2, comma 0, which would be this point. And at the same time, we should recognize, let's try something else. What if x is 3? I don't even have that on here, do I? But if x is 3, then what would y be? It would be, let's see, 3 squared, that's 9, minus 4, it would be a 5. So out here somewhere where x is 3, our point's way up here where y is 5, isn't it? Now, we actually have the same points. Remember, we're going to get the same results whether we use a positive 1 or a negative 1, a positive 2 or a negative 2, a positive 3 or a negative 3. We're going to get those same values, aren't we? So we'd have a negative 1, comma negative 3. When x is negative 2, we would have a 0 for y. And when x is negative 3, we would have a 5 for y, so roughly here. So the graph of this parabola, I'll sketch in, is going to look something like this. Now, you've probably already noticed that my x-axis and my y-axis have different scales, and I only did that so that it wouldn't be so skinny and crammed in, it would be hard to read. But of course, now we're not going to have a real reflection of the area because I have two different scales, but we'll get the idea of how this process goes. Okay, now, there's our first function, f of x. Now we need to graph our second function. And our second function is just g of x is equal to, okay, so I'm going to get this separated out. Now I'm working on graphing that second function. And so that second function, which is g of x equal to x minus 1, well, we recognize that's just a line, isn't it? And so that doesn't take much work at all. We just need 2 or 3 points. So we might as well choose a value like x equals 0, and we'd calculate y to be negative 1 real quickly. So that goes through this point, doesn't it, right here? And then we could choose x equal 1, and when we do, we'd get a y equal 1, wouldn't we? That'd be this 1, comma 1. And so that'd be this point right here. And that's probably enough points, but let's go ahead and maybe try another one, like when x is 2. Then when x is 2, what would y be? Oh, it'd be 4 minus 1, which would be 3. So when x is 2, y would be 3. So that's roughly here. And now we'll draw in this line. And we'll have something that looks roughly like this. Now, what we're supposed to do, we've got our 2 graphs. Now we'll find the area of the region bounded by those 2 graphs and the vertical lines x equals 0 and x equal 2. Well, now x equals 0 is right here, isn't it? And x equal 2 would be the vertical line that would go right along here. Now, of course, it goes up higher than this, and it goes lower than this, but I'm only showing the region, the line segment between the two graphs, because we're looking for the area of the region that's bounded by those two graphs and those two vertical lines. So this is the area, this is the region we're looking for the area of. Okay. Well, what we need to do next is to understand how we're going to calculate that area. And so what we'll do is, like we kind of did before with the line segments, we'll look at a representative rectangle, of course, that is infinitely narrow. So this is the rectangle that I'm considering. Now, to calculate the area, what I know I'm going to do is I'm going to add up all of these rectangles, the area of all these rectangles. And of course, the rectangles are going to start over here where x is 0, aren't they? And we're going to move those rectangles along through that area, through that region, until we stop over here where x is equal to 2, because that's the boundaries for where that region is. So we're going to integrate from 0 to 2. And this integral is adding up the infinite number of infinitely small rectangles, or the area of those infinitely small rectangles. So what we have to do is come up with the area of this single representative rectangle. Well, the width, of course, is going to be that dx, infinitely narrow. It's the height that we have to be concerned about. See, it's that height that we're worried about. And that height, we have to say, okay, take the highest y value and subtract the lowest y value. But notice that the highest y value is defined by that line. See, and that's the g of x, isn't it? And the lowest y value is where that parabola is, and that y value is calculated with f of x. And so, like I said, we can't assume that we're going to say f minus g, because this height will be the highest y value f of x minus the g of x minus the lowest y value of f of x. See, there's the highest, that's g of x. There's the lowest, that's f of x. Well, I've got a little out of whack. So the way we set this up then will be the integral of g of x, the highest, minus f of x, the lowest. That's the height. And then the width is dx. Now, after we've done that, it's a matter of putting in the actual functions. And g of x is the function is actually represented by 2x minus 1. So that's the g of x. And we're going to subtract from that the f of x. And the f of x is x squared minus 4. And then don't forget our dx. So what we'll do at this point is we'll actually simplify algebraically what we have in those brackets. And you see that we'll end up with a 2x, and we'll end up with, I see, a minus x squared, and then we'll have a minus 1 and a plus 4, won't we? I should do better than that. I apologize. This will end up being a 2x minus 1, and then a minus x squared, when we distribute that negative sign, and negative of negative 4 is plus 4. So that ends up being a 2x and a minus x squared, and what, a plus 3. Now, that's not really in a very good order, so I'll probably, if it were me, I would have rewritten it maybe as maybe a 3 plus a 2x minus an x squared. I'll have it in some order, and since I have that negative x squared, I'm putting it at the end, but it could be at the beginning just as well. Okay, well, let's go to the next page here so that we can finish this without trying to cram things in. So let's do that right now. Okay, of course, the way we do the definite integral now, and remember, we're still working on the area. This is the area that we're calculating, isn't it? We've already got everything set up. The way we do the definite integral is first we need to find the indefinite integral. and then we evaluate it from 0 to 2. And sometimes we have to go off to the side and do that because the indefinite integral is so complicated. But the fact that we have a polynomial makes it pretty easy. And so we'll just think, well, what's the integral of 3? Well, that's a 3x. And what's the integral of 2x? Well, that's just x squared, isn't it? It would be 2 times x to the power 1/2, power 2 with a 1/2 in front of it. But clearly, we can see that if we take the derivative of x squared, we get 2x, which is what we started with. Now over here with the derivative of x squared, we have the minus sign in front of it. We'll increase the power by 1, but we have to offset that with the reciprocal of the new power in front. And so it'll be minus 1/3 x cubed. There's the indefinite integral we're going to evaluate from 0 to 2. So that means we're going to first substitute a 2 in for all of the x's, and then we'll subtract what we get when we substitute an x in. And you'll probably already recognize, a 0 in. And since all the terms have an x in them, then when we put a 0 in, then it's going to, can't talk and show you at the same time. Our x is 2 first, isn't it? So I'm substituting 2 for all of the x's, and then we'll subtract, and we'll substitute a 0 in for all of the x's. And we kind of like that because when everything has an x and we're putting a 0 for the x, then of course all of that goes to 0. Everything here is 0, so it just results in a 0. And so that's less work for us to do. 3 times 2 is 6, plus 2 squared, which is 4, and 10 cubed is 8, so it's minus 8 over 3. And of course that's 10 minus 8 over 3. And with just a little bit of calculation, it wouldn't take us anything to figure out that that is 22 over 3. And remember, we'll leave them as improper fractions, but sometimes it's nice to know, as a decimal or as a mixed number, just how much that is. That's 7 1/3, and of course these are square units, aren't they? Because we're talking about area. So the area of the region involved is 7 1/3 square units. Okay, I think what I want to do next is the same kind of problem, but it has a little twist to it that we're going to need to be concerned about. Hold on, and we'll start this up on the next page. Actually, I think I'll start a brand new problem.